So we're going to now learn about evaluating these limits. So the statement, the limit of f at x as x approaches a equals L means the limit of f at x as x approaches a equals L. So that's how that is read. The value of f at x will be closer to L as the value of x comes closer to a. So we're going to see as we go through these that sometimes you'll be asked to evaluate a limit where there are no non-permissive values, like this first one. Non-permissive values will come when you have denominators, and sometimes when you have radicals is where we have non-permissive values. But this is not a rational function, it's just a polynomial function. So what this is really asking, it's asking what is the value of x squared plus 2x minus 3, what is the value of that approaching as x gets closer and closer to 5? So what we could do is we could choose numbers that get closer and closer to 5 and evaluate that function for those numbers. And as long as that function is approaching an integral answer, we could guess what the limit is. However, in this case, because 5 is not a non-permissive value, we can find the limit just by letting x equal 5 in the function. So this one can be found by letting x equal 5, because 5 is not a non-permissive value. So that'll be 25 plus 10 take away 3, which is 35 take away 3, which is 32. So that's the value of that limit. Remember, it's not asking what is the value of the function when equals 5. It's asking what is the function approaching as x gets closer and closer to 5. That's really what a limit is. But in this case, because 5 is not a non-permissive value, we can do it just by straight substitution. If the limit of f at x as x approaches a equals f at a, which is what we just did, okay, the limit was found by letting, in this case, x equals 5, then we say that f at x is continuous at a, and we can show this graphically. So this next question says determine the limit of 3x minus 4 as x approaches 2 and graph the function. So you can do it two different ways. We can graph the function first and state the limit second, or we can state the limit first like we just did in the last example by letting x equal 2 and then graph it after. But let's graph it first. So the function is defined by 3x minus 4. That's a linear function. It's a line that has a y-intercept of -4 and a slope of +3. So we can graph it. Y-intercept of -4 and a slope of +3. So we would rise 3 and run 1. Rise 3 and run 1. Rise 3 and run 1. We could also rise -3 and run -1. That would also give us points that line up with all the other points that we have. And so we can graph this line. There's a line y equals 3x minus 4. And we want to find the limit as x approaches +2. So where is that on the graph? X equals +2 is right there. As x gets closer and closer to +2, the graph will approach that point right there, where in this case, y also equals 2. That is the point 2, 2. As x gets closer and closer to 2, the value of y will approach this point here where y equals 2. So the limit as x approaches 2 of 3x minus 4 is also +2, because that is the value that y is approaching as x gets closer and closer to 2, which if you look at the function, you let x equal 2, you get 3 times 2, which is 6, take away 4, get your answer. But as I said, in most cases, when you're asked to evaluate a limit, the number that x is approaching will be a non-permissive value. So you might use a graph to see if you can figure out what that limit is. Or we'll also do them algebraically using some of those tricks that we've been talking about. Quite often you'll have to factor. Maybe you might have to multiply top and bottom by conjugates. So we'll do lots of examples where we see that. But they can all be done using this graphical approach as well. So from that graph, there are no non-permissive values. The limit is continuous over the domain of real numbers and also at 2, which is what x was approaching. There are no breaks in the graph, so we say it is continuous. But this next one, limit as x approaches 2 of x squared minus 4 over x minus 2, we cannot do this out by substitution because 2 is a non-permissive value. So you could do it by setting up a table of values, which would lead to a graph. So you can see the table of values there, right? We're finding the limit as x approaches 2. So you can see I started first by using x values below 2, but getting closer to 2. And then I use values of x that were greater than 2, but also getting closer and closer to 2. And so if you let x equal all those values, you can see the corresponding y values. And it's pretty clear by looking at the table of values that the limit as x approaches 2 of this function is 4. That is the value that f at x is approaching as x gets closer and closer to 2. So that would be the value of that limit. So you could do it by setting up a table of values. And as long as the value of the limit is an integer, again, you can pretty much guess what it is. And then you could also go one step further and draw a graph from that table of values. But in this case here, because 2 is a non-permissive value, there would be a spot there where the graph is not continuous. We'd say it's discontinuous. And so let's look at that graph. So you might remember from 30-1, you learned about graphing rational functions. And we saw that when there was a non-permissive value, there were two things that would happen. Either you'd have a single point of discontinuity, a hole in the graph, or there was a vertical asymptote there. And the way we determined which of those two cases we had was we simplified the expression. If we could cancel the factor that gave us the non-permissive value, then we had a point of discontinuity there. If after factoring we couldn't cancel the factor, the denominator that has a non-permissive value, that meant that there was a vertical asymptote there. So let's see what happens here. If we factor, so we have the limit as x approaches 2. The numerator is difference of squares, so we can factor that, x plus 2, x minus 2, all over x minus 2. And now you can divide top and bottom by a factor of x minus 2. Essentially, you're dividing them both by x minus 2, which leaves us a 1 on the top and a 1 on the bottom. And so we are left with the limit as x approaches 2 of just x plus 2. So again, because the x minus 2 on the bottom canceled, that means there's a point of discontinuity at x equals 2. So the graph of the original function will be the same as the graph of our simplified function, the line x plus 2, but with the same restriction. X cannot equal 2. And so there would be a point of discontinuity at x equals 2. So let's graph this line. That line has a y-intercept of plus 2 and a slope of positive 1. So we'd rise 1 and run 1. So that point will be on our graph because that's not where x equals 2. But if we rise 1 and run 1 again, this is the point where x equals 2. That's our point of discontinuity. There will be a break in the graph, a hole in the graph. And then it picks up after that by rising 1, running 1, rising 1, running 1. Or we can rise -1 and run -1, rise -1 and run -1. That works as well. So now we can draw our graph. It's a series of two lines. And it looks like that. But again, just like we saw in the table of values, the closer that x gets to a value of positive 2, this graph will approach this point with the open circle, that's our hole in the graph, where y equals 4. That is the value of that limit. That is what y is approaching as x gets closer and closer to positive 2. Okay? So same thing with this next one. If we wanted to evaluate that limit, the first thing we might do is let x equal 3 and make sure or find out if it's non-permissive or not. So when x equals 3 in the bottom, you're going to have 9, take away 12, plus 3. When you let x equal 3, which is 0. So this has a denominator of 0. It doesn't matter that the numerator is also 0. It doesn't matter. Anything divided by 0 is undefined. There's only one person that can divide by 0, and who's that? Chuck Norris. The only one. No one else. Chance. Look up Chuck Norris. Find out who he is. Okay? So we have to do something to this function so that we could find out what the limit is. And let's try and factor it. So we have the limit as x approaches 3 of x minus 3 over, so the denominator would factor to x minus 3, x minus 1. And the x minus 3's would cancel. So we would have the limit as x approaches 3 of 1 over x minus 1. So this graph, and we'll look at it, we'll see what it looks like on our graphing calculator. Now again, you won't be able to use graphing calculators on your quizzes or tests. So in that case there, you'd probably use a table of values to see what this graph looked like. Okay? However, this would have a non-permissive value of 1, and because that x minus 1 factor is there, didn't get rid of it, that means there would be a vertical asymptote at x equals 1. You also might remember from the work in Math 30-1 that for these vertical, or for these rational functions, quite often the x-axis is an asymptote. The x-axis is where y equals 0. You see, no matter what number you put in for x, for that function, 1 over x minus 1, you can never get an answer of 0 for that. The only way you can get an answer for 0 from a rational function is if you can somehow make the numerator equal 0. 0 divided by something will give you an answer of 0. But you can't make the numerator 0. The numerator is a constant, positive 1. The only way a rational function will equal 0 is if the numerator can equal 0. And in this case, it can't. So, whoops, try that again. Y can never equal 0, so the x-axis is an asymptote. And so, like I said, we can use our graphing calculator to see what this looks like. Again, you might remember from 30-1 that these rational functions usually had 2 parts to it. One part would be in one quadrant, and the other part would be in the quadrant directly across from that. So you could use a table of values to get some points for this graph. So let's do that, because again, we're not supposed to use graphing calculators for quizzes or tests, so let's do this using a table of values. So if we chose a couple points to the right of the vertical asymptote, for example, when x equals 2, the vertical asymptote is at x equals 1. So what do we get when we let x equal 2? So f at 2 would be 1 over 2 minus 1, which is 1 over 1, or 1. So the point 2, 1 will be on this graph. We can actually find the value for f at 3 because with the simplified function, 3 is not a non-permissive value. That is what the limit is approaching. For the original function, 3 is non-permissive, but for a simplified one, it's not. So we can find out what we get when x equals 3. That'll be 1 over 3 minus 1, or 1/2. And that is our point of discontinuity. So we'll draw a tiny circle there. That is our point of discontinuity because 3 is a restriction for the original function. We got rid of that factor of x minus 3 when we factored and simplified, but that tells us that 3 is where we have a point of discontinuity. So this is really all we need to know to see what the first arm of this graph looks like. It'll go through that point. It'll hit the point of discontinuity. There will be a break in the graph, and then it'll continue on after that, approaching that asymptote. So now let's generate a couple points to the left of the asymptote. Again, the asymptote is at x equals 1. So what if we did f at 0? F at 0 would be 1 over 0 minus 1, or 1 over negative 1, which is negative 1. So we have the point 0, negative 1, which is there. And really, that's all we need to know. Once we know that that point is there, the rest of the points will be in that lower left quadrant of this graph. So this graph would look something like this. Again, it approaches the asymptotes to the left and going down. However, we were wanting to find the value of this limit. And we can see that the limit as x approaches 3, this graph will approach that point of discontinuity, which we found to be positive 1/2. So that is the value of that limit. That is the answer to this. The limit as x approaches 3 of x minus 3 over x squared minus 4x plus 3 is positive 1/2. Because that's where the point of discontinuity is. It is the point 3 comma 1/2. This graph has two places where it's not continuous. One of them is at the vertical asymptote. It's a break in the graph where if you're drawing it, you got to stop drawing and then pick up your pen or pencil, move it somewhere else, and start drawing again. And then our second point where the graph is not continuous is that point of discontinuity. Again, if you're drawing the graph, you have to stop once you get there, pick up your pen or pencil, move it, and then start drawing after that. Now, you didn't need the graph to find the answer, right? Once we simplified the expression, you can let x equal 3. And that's what we did to find where that point of discontinuity is. So you don't have to graph to find the limit. You could have stopped and done it algebraically by doing exactly what we did. We generated a table of values. One of the points we chose was where x equals 3, because it's not a non-permissive value for our simplified expression, only for the original. But the graph of the simplified has to have the same restrictions as the original function. So that's where we had to include that point of discontinuity there. So again, by factoring, getting rid of that factor that gave us a non-permissive value, we could then just use substitution to evaluate that limit. But we had to get rid of the x minus 3 on the bottom before we could do that. And so that's what we did. So that's what we'll do from now on. We're not going to have to draw graphs, but we always have to keep in mind kind of what the graph will look like. In most cases, the value that the x is approaching will be a non-permissive value. And so that's where you want to start with. Check to see if it's non-permissive or not. So for this first one, when x equals 2, the denominator will be 2 squared plus 3 times 2 is 6 minus 4. You're going to get 4 plus 6, take away 4, which is 6. So 2 is not a non-permissive value of that function. So that means that we could find our answer just by substitution. We can let x equal 2 in the function. So the top will be 2 minus 4. We already know the bottom is 6. 2 minus 4 is negative 2 over 6, or negative 1/3. That's the value of that limit. So you can see this one would be a little harder to guess by using a table of values because the limit is not an integer, it's a rational number, a repeating decimal. So it would be more difficult to guess what that limit is, what the value of that function is approaching as x approaches 2, but we don't have to guess anymore. Okay? So there's the value of that limit. Okay, going on to the next one. Again, we'll start by checking to see whether or not 3 in this case, because that's what x is approaching, is non-permissive or not. So 3 squared is 9, plus 2 times 3 is 6, take away 3. 9 and 6 is 15, take away 3 is 12. So again, 3 is not a non-permissive value for this. We can do this one just by substitution. We already know the denominator works out to be 12, so you're going to get 2 over 12, which is 1 over 6. That's the value of that limit. Again, that one would be very difficult to determine just by guessing. By using a table of values, letting x get closer and closer to 3, it's going to approach a value of 1 over 6, which is a decimal. I think it's 1.16 repeating, yep. Okay, so that would be really difficult to guess from using a table of values. But again, we don't have to anymore. But this next one, we cannot do it by substitution because 1 is a non-permissive value. Also in this case, there's nothing we can do algebraically in order to get rid of the x minus 1 on the bottom. So in this case, we really have no choice but to draw a graph, which essentially we would get from a table of values. Now, 1 is a non-permissive value, and again, we can't get rid of that. That x minus 1 factor is nothing we can do to get rid of it, which means that there will be a vertical asymptote at x equals 1. So, we're going to graph this by using a table of values. Once again, this is a rational function. Okay, so we are going to have a horizontal asymptote here, but it is not going to be the x-axis. And again, you might remember from 30-1, when you have a rational function, look at the degree of the top and bottom. If the degree of the top and bottom are the same, which in this case they are, they're both x to the power 1s on top and bottom, you can find the equation of the horizontal asymptote by dividing the coefficients of those x terms, the highest power terms. The coefficients of the x's are both 1, and 1 divided by 1 is 1, so our horizontal asymptote will be at y equals 1. And now we will generate a couple points on either side of that vertical asymptote. Okay? On either side of that vertical asymptote. So example, when x equals 2, you're going to get 2 plus 3 over 2 minus 1. That'll be 5 over 1, or 5. So the point 2 comma 5 is on this graph. And really, that's all we really need to know for that quadrant. That tells us that the graph will come down and approach the asymptote and look something like that. On the other side, let's choose a value to the left of positive 1, again, because that's where our vertical asymptote is. Let's find out what f at 0 is. So you're going to have 0 plus 3 over 0 take away 1, which will be 3 over negative 1, or negative 3. So the point 0 comma negative 3, our y-intercept is right there. And again, that's all we really need to know. We could find our x-intercept by letting y equal 0 if we wanted to. Remember, a rational function equals 0 when the numerator equals 0. In order to make the numerator x plus 3 equal to 0, you'd have to let x equal negative 3. So that's where our x-intercept is, at the point negative 3 comma 0. This just helps us draw a more accurate sketch to the graph. It'll look something like this. we want to know what the limit is. What does this graph approach as x gets closer and closer to 1? If we look at this graph from the left side of 1, the graph is going downwards forever. On the left side of 1, the graph is going downwards forever. It's approaching a value of negative infinity. But on the right side, as you get closer and closer to 1 from the right, the graph is going upwards forever. It's approaching a value of positive infinity. In this case, the limit does not exist because the graph is approaching different values on either side of x equals 1. And that's going to happen sometimes where the limit does not exist because the graph is approaching different values on either side of 1. So in this case, we say that this limit does not exist. Now, as we go through this chapter, we will talk about one-sided limits, where you might want to find only what is the graph approaching on the left side of the non-permissive value or the right side of the non-permissive value. Those will exist. But in this case here, because we want the limit as x approaches 1 on either side, and because the graph approaches different values on either side, the limit does not exist. Sometimes that happens. Okay? So looking at this one, again, what we've done first is check to see if, in this case, 2 is a non-permissive value. 2 squared is 4. Minus 3 times 2 is 6 plus 2. That equals 0. So 2 is a non-permissive value. We cannot do this one by substitution. If you look at this rational expression, you should recognize that the top can be factored as a difference of cubes, and the bottom can also be factored. So we're going to do that to see if we can get rid of the part of the denominator that makes 2 non-permissive. So again, the top is difference of cubes. Remember how we factored difference of cubes. The cube root of x cubed is x. The cube root of 8 is 2. To get the terms for the trinomial, you square the x, you multiply the 2 and the x together, and you square the 2. And then you have to remember the sign pattern for difference of cubes. It was minus, plus, plus. The denominator. So hopefully we're going to get a factor of x minus 2 on the bottom as well so that they will cancel. And then we'll get rid of the part of the denominator that makes 2 non-permissive. And we do because that quadratic on the bottom factors to x minus 2, x minus 1. Two numbers that multiply to get positive 2 and add to get negative 3 are negative 2 and negative 1. And again, we can divide top and bottom by a factor of x minus 2. So we're left with the limit as x approaches 2 of x squared plus 2x plus 4 over x minus 1. Now we have a non-permissive value of 1, but it doesn't matter because we want to find the value of this limit as x approaches 2. So now we can do it by substituting 2 into what we have left. So 2 squared is 4, plus 2 times 2 is another 4, plus the last 4, over 2 minus 1. That gives us an answer of positive 12. So there's the value of that limit. So what would we see happen if we graph this function? Well, the graph of the simplified function has the same non-permissive value as the original function. It would have a vertical asymptote at positive 1 because that's a non-permissive value for the simplified expression, right? We still have the denominator of x minus 1 there, so x can't equal 1. But that means there's a vertical asymptote at 1. It also means that there's a point of discontinuity at 2, 12. The value of the simplified function when x equals 2 is 12. But we have to keep the same restrictions as the original function, so x can't equal 2, therefore y cannot equal 12. There would be a point of discontinuity there. But we don't need the graph to know that. You do it algebraically. So looking at this next one, 0 is a non-permissive value for h. Not always going to have variable x in there. Variables can be whatever they want to be. But 0 is a non-permissive value, so we need to do something to get rid of the h on the bottom, and that something, again, will be factoring. The top is a difference of squares. The square root of 2 plus h all squared is 2 plus h. The square root of 4 is 2. One's a plus, one's a minus. So when I simplify this bad boy, I'll get the limit as h approaches 0. I don't know why I wrote 2 there. It should have been 0. So on top, I'll get h plus 4 as my first factor. But the second factor, because the 2's will cancel, I'm just left with h, which will cancel with the h on the bottom. And so we are left with the limit as h approaches 0 of just h plus 4, which now we can let h equal 0, and we get an answer of positive 4. That's the value of that limit. So in this case here, if you were to graph that function, there would be a point of discontinuity at the point 0, 4. You can graph the simplified expression h plus 4. That's the same as x plus 4. It's a line. But because we got rid of the factor of h on the bottom, we have to hold the same restrictions for the original function as we have for the simplified one. So 0 is a non-permissive value, and there would be a point of discontinuity there because we got rid of that factor of h on the bottom. It's still a restriction, but there'd be a point of discontinuity here at the point 0, 4. Okay? All right, so we'll stop there for today, and we'll pick this up again on Monday. You can work on these questions. So we'll do some more of these on Monday, evaluating limits, again using some of the tricks that we've learned about already. And then I think we're having a quiz on Tuesday just on limits. Okay, I'll confirm that and let you know, but I think that's the plan. Did you guys all get an email yesterday from me through PowerSchool? Okay. So I'll send, I always put the quizzes on the backboard there, but I also try and remember to send out the emails to let both you and your folks know that you guys have assessments coming up. So again, really important that you do these. The practice is very valuable so that you get good at it. I will post the solutions to today's assignment on Google Classroom. Okay? Probably on Monday when we do the second part of this, I'll probably take that one in for marks. So do the practice, okay, Sharon? Don't be a slacker. You're going to stay in this course, aren't you? Because you're having so much fun. I know you are. Do all the plugins have those USB ports on them? Not all of them? Is that right? Just the cool teachers got them? How do you spell what? Luggage. Luggage, I think. Yeah. Right. No, we did a review assignment. Well, what did I?
remember you telling me to, when I come back, try to make it test.
Yeah, I don't think I realized that it was at the end of the semester would be over when you came back. Let's have a look here and see what I did with that. Hmm.